Anybody doing here a PhD in graph colorings? Oh, okay. So what kind of colorings are you doing? Total coloring. You? Injective one? Subset square. Square coloring. A subset square. A new variation. Okay. And you? Roll? I don't mind. So there are so many colorings you see. Yes. I know only few one. So okay, we can start, So, when I have to watch you, I have to put my glasses, yes. Then I watch good. But if I want to watch here, then I have to put them down. So it's not easy when you're old. Then I'm forgetting very fast. So maybe I forget something to tell or how to prove it, yeah. And when you're old, you get tired very easily, yes. So it will be intensive course for me. This will not be easy job for me. Okay, I'm asking to give some application of graph colorings. Personally, I never did it application of graph colorings, but I have a look on the internet, and mainly the application of this type. We have some tasks, and they are usually conflicting tasks. Some of them are in conflict, some of them are not. Conflicting tasks, yeah. So this conflicting in parentheses because, and we have resources. Like one such example is, so in order to solve the task, we should apply the resources. But some of these tasks are in conflict, so cannot happen in the same time. So our task will be vertices V1 or T1, T2, T3, T4, T5, and so on. If two tasks are conflicting, what we do? We put an edge between, yes? So these two are conflicting. Cannot happen in the same time. These two are conflicting. Maybe these two are conflicting. Maybe these two are conflicting. And so on. And so we get a graph. Now we would like to solve this task by applying our resources. So each resources will be actually, I don't know, something that solve the task, but which can be applied only once at a time, yes? So minimum number of resources we need will be actually graph coloring. Chromatic number, the number of colors we use it. Yeah. Why? Because when we color with red, with blue, with green, if we have a look in the color classes, inside there will be only this color class will be independent set. This color class will be also independent set, and this one too. So we can apply for each of these color classes one resource to solve it. One such example is airplane flying company. Let's say, I don't know so much the Indian cities, but let's say Europe, yes, our company has to service like flights. Usually they are return. London, Barcelona, and usually they are going the same time. And maybe it want to make the service from 12 o'clock from noon to 2 hours flight in one direction, 1 hour, 2 hour breaks, and going airplane back. It's like 2 hours more. It's like between 18 and 16. Yes, we want to make this service fly to London, Barcelona, London, and our airplane will be busy from noon to 6 o'clock afternoon, yes. Then we may have some other one, maybe Paris, or let's say we start flying from London, yes? Let's say all the flights go from London. Let's say we are airplane company operate from London, yes? Then we have like, no, this one. Then we have maybe 9 o'clock, London, Dubai, yes? Dubai, yeah? And then we may have London, let's say this is from 8 o'clock until 20 o'clock, and then we may have flight London, Moscow, and so on. So each of these flights will be a vertex. And then we connect, let's say London, Barcelona, let's say London, Dubai, yes, London, Moscow. And then we put edges in between if they are in conflict, happening in the same time. And when we color the graph optimally, the chromatic number will be actually the minimum number of airplanes we need to make all these services. Okay? So this is, I call it like a task with conflicts and resources. Many of these, in this way, you can have many applications. Another application, which I know it's real, it's call it a register allocation in compilers. Allocation in compilers. This is very tightly connected with the microprocessor of the computer. So the compiler, what do? Compiler takes something written like in some language like Java or I don't know what, and then turn it into assembler, turn it into machine level language. In this machine level language, the machine has some registers like R1, R2, R3. I don't know. When I was student, we studied like computer processor up to 10 registers or 20 registers. Maybe they have now 100 registers. I don't know. They have different, many cores nowadays, the computer CPU, and they have maybe 100, yes. And now, in your program, you define many variables. X, Y, some are integers, some are string, whatever. And because these variables, you very often access to these variables, you want these variables, the value to have them on the registers, yes. So this is for some variable v1, this is for x, this is for y, you define it so. And so in different time, to register will be assigning different variable. You know, now some variable is in conflicting, like they can happen in the same time and so on. So if two variable can be accessed in the same time, you cannot assign them to the same register. So what your variables will be now the vertex of the graph, and if I have, let's say, these two variables defined in the same procedure, which can be in the same time accessed, we put edge between. The number of colors will be here, we apply, will be in a way the number of registers we can use, yeah? So we hope we have less. Otherwise, if the coloring, chromatic number is bigger than the number than the registers, then we put some values on the stack and somewhere else in the memory and then come access them, putting that back, and that make the program very slower. So I know that some editor, maybe, do you know Zdenek Dvorak? Anybody heard about Zdenek Dvorak? He's a very good graph theoretist, colleague of mine. Zdenek Dvorak from Prague. He's editor in JCTB. This is one of the best journals in graph theory. So when Zdenek Dvorak was student, he was working for optimizing the compiler GNU C++, I think, yes, for GNU C++, or maybe just GNU C, I don't know. They are very similar. So he was working in optimization. I don't know if he applied really directly coloring. So next time I meet, I will ask him. So I meet him once in a couple of years on some conference, and next time I meet, I will ask him. So there are many such applications. One more application is, let's say, frequency assignment, or channel assignment. In wireless networks. So this is something connected with the mobiles. When the mobiles appeared, it suddenly become popular. There appeared different colorings. Just also in England, they used to call them coloring for money. So like coloring for money. Just for fun, they say. So how it comes, like, you know that the spectrum of frequency is bounded in the air. So I'm not physician, I don't know these things very much. And now, if we have two mobiles close to each other, and the central, two mobiles, N1 communicates with some person T1, and MT communicates with some person T2, let's say. Now, if these two telephones are close, let's say in the same room, yeah, so somewhere close, then N1, T1, they connect between the central somehow, let's say, and M2 connects with central, yes. These two maybe are far away, but these two, let's say, are close. And because these two are close, if they get close frequencies, which are very close to each other, then it will become interference. So there will be noise. M1, mobile 1 will have noise from mobile 2, and mobile 2 will have noise from mobile 1. So if two telephones are close, let's say, enough, they should get frequencies which are far away. And this is called frequency assignment. So you want you have a location of some mobiles or some things that communicate with the central through some frequencies. So you want to spread this frequency to these mobiles so they don't disturb each other. And this frequency are the colors, yes. And this M1, M2, T1, T2 are the vertices. Now, I don't really know how this in the practice they do that in the companies, yes, or how they solve these problems. So, but this is somehow considered like a kind of coloring problem. And then some other application, I just ask ChatGPT, and it even says quantum circuit optimization, DNA sequences, logic circuit designs. But this is the same type of application. We have some tasks and we have some resources. And now, going to little bit different, you know, when I was flying now from Frankfurt to Delhi, there was a lady stewardess. Each time she had a free time, she was doing Sudoku. The Sudoku is a kind of coloring related games. So we have at least one, but I think there are several or more coloring related games. So this is games. Some games are related with colorings, puzzles and games. Yeah? Second, social networks. Here you can use color in a usual way to color the vertices in order to visualize the network. This is one thing. Second thing, you can use some kind of coloring procedure to obtain the communities. Let's call it area of research. Physicians do that a lot. Community identification or something like that. So to get these groups, like under certain conditions, you can group the vertices or the people in some social network, yes. And of course, map coloring, usual map coloring by which appear it, like we color a map with several colors, like India, we can color it with 4 colors, United States with 4 colors, and so on. Okay, this is my intro. Now, the genericity, I was supposed to teach the genericity, but it was taken, yes. So we start with critical graphs. So if you are serious about the graph colorings, you should learn the critical graph. This is the essence. So actually there are 2 types of critical graph, edge critical graphs and vertex critical graphs. I will deal more with edge critical graphs. So how is defined it? Graph G is K critical, K is some integer, if first chromatic number of G is K and second, for every proper subgraph H of G, we have that chromatic number of H strictly smaller than K. Now you tell me some critical graph. Do we know some critical graph under this definition? Let's take K4. K4. This is K4. What is the chromatic number? Chromatic number is 4. But if we delete some H, or maybe even something more, if we delete some H, I can put here red immediately, yes? And I have 2 more vertices, then immediately I have H is some subgraph, proper subgraph, then it's at most 3. So we can easily see that KD is day critical. Okay? Okay, let's see. This is, let's see for D1, for K1, let's say K1. What is the only critical graphs? It's K1. This is the only critical graph. We don't have subgraph. It uses 1 color, and we don't have subgraph. This is only 1 critical graph. For K2, can you help me? Yes. This is the edge. Yes. Whenever we remove the edge or some vertex, automatically then the edge also remove it. We have 1 vertex. We need only 1 color. Is the only 2 critical. Okay, for K equal to 3. Sorry? Yes, exactly. This is the only odd cycles. So this is the triangle. This is 3, 5, 7 cycle. 7, and so on. This is the 3 critical graphs, yes. Is there any other 3 critical graph? Are these all critical graphs? Do we know some more? Because it is the 3 critical, let's say G is a 3 critical graph, G is 3 critical, and is not odd cycle. Is not odd cycle. And if it is not odd cycle, okay, but what's mean? The chromatic number of G is 3. So it has some odd cycle. If it has no odd cycle, its bipartite graph is 2 colorable. So in G we have, this is G, and we have some odd cycle here, yes? Let's say some odd cycle. Let's say. Now, if we have some edge somewhere here, we can remove it, and the chromatic number will not go down. We have the odd cycle inside, yes? So 3. And this edge can be also here maybe, even if you remove this edge, or the edge should be like this. So we don't have any other this kind of pinky edges. We have only these blue edges. This implies that our 3 critical graph, I would not write it too long, lengthy, G is odd cycle. So these are all 3 critical graphs. Okay? What about K4? So far we characterize 1, 2, 3. Can we characterize 4? No, we cannot characterize 4 because behind are some NP-hard problems. So, in a way, these 1, 2, 3 cases are not interesting for us. Whenever I mostly say K, I mean at least 4. I don't worry about how I delete this. Whole. So this is not interesting, yes? Studying K critical graphs is interesting for K at least 4. Okay? And K critical graphs were defined by Dirac. In Dirac in 1951. They were defined it. He was studying coloring, PhD was doing, yes, and okay. Now some property about critical graphs. Properties. I will assume K is at least 4, yes. Maybe also work some smaller K, but they are not interesting, yes. First property, G is K critical. First property, minimum delta G, small delta G, this is the minimum degree, is at least K minus 1. Property B, Kk is the smallest K critical graph. There is no, how I write it, okay, there is no, okay, there is no K critical graph on K plus 1 vertices. And D will be no K critical graph has a click cut. We will define what is click cut. In particular, where they are too connected. This is here. Here we use that K is not is at least 3 as, but we assume that K is at least 4. Okay. Can you help me? We proved A. We claim so how we prove it? Look, we have a graph G, and we have here vertex of degree smaller or equal K minus 2. We go by contradiction. We have a vertex of degree K minus 2 or smaller. Okay? Then consider graph G prime. This vertex is V. What is chromatic number of G prime? Because we remove from G a vertex, chromatic number from K will go to K minus 1. Actually smaller or equal K minus 1. But it is easy to see that it is precisely K minus 1. So, okay. Okay. So we remove that. So here is G prime minus V. So this is G minus V. We color it. Color with K minus 1 colors. Can you guess what I'm going to do now? I take vertex V and put it back. I take vertex V and put it back. Here is some color, which will be forbidden for me. Let's say color 1. Here is some other color, maybe the same one. It's harder, it is different one. Maybe another forbidden color. How many forbidden colors are you going to have? When you're out, you're also not very here. How much? Delta? K minus? Yes. K minus 2 forbidden at most. Yes. Forbidden colors. So I can use in the worst case, one of these k minus 1 free colors, use color, the free color that is free, or not use it if you want, from interval here n-1 colors, and I on this pinky vertices I spent n-2 k minus 1. Sorry, here is k. Here is k. Yes. So then I have free color to color it. Yes. This is how. Do I'm going too slow? I can go much faster. Huh? Is this okay? This, you tell me if I'm too slow. You say, Professor, you're boring. Let's go faster. You know. Okay. This is proof of A. If we can have a smaller vertex, a smaller degree, we can remove it, color the rays with k minus 2 colors, put it back this vertex, we can also extend it, and we can use like at most k minus 1 colors actually, which is contradiction that graph G has chromatic number k. Okay. B. K is the smallest. It's K critical. Graph. KK, yes, sorry. KK is the smallest K critical graph. Anybody knows how to prove it? I think it's so simple that I don't know how to prove it. So, can we have less than K vertices? Let's say G is smaller than. Then, if G has less vertices, can it be K critical? You need K colors to color it. Chromatic number should be K. If chromatic number of G is K, then the number of vertices must be at least K. Can it be smaller? Okay. So what is our hope? Our hope is G, actually K minus some edges. KK, we obtain G from KK by removing some edges. We remove this edge, maybe another one or another one. We remove this. Even if we remove one, look, if we remove this, let's say just one, this one, then I can put color here 1, 1, 2, 2. I will not need n colors. I will do it with n minus 1 or n minus 2 or n minus 3. So it's n chromatic number of G is strictly smaller than K. Sorry. And it's easy to prove that it's not critical as well, but it's this way it's easier. Okay, C, you must help me for C. What was C? C was no K critical graph on K plus 1 vertices. So suppose they exist. Suppose G is such. G is K plus 1 critical, no, G is a K critical graph on n plus n vertices. Because G is on K plus 1 vertices, we can obtain G, we can construct G or we can construct from k plus 1, we take the complete graph on k plus vertices. This is the number of vertices G has it, and remove some edges. And remove some edges. So maybe I draw it here. So here is our k plus 1. So the number of vertices is okay. The number of complete graph on k plus 1 vertices, we say, let me write it more clear, k plus 1. The number of vertices is correct, 1, 2, 3, 4, up to k plus 1. But because it's not k plus 1, k plus 1 is k plus 1 critical, so we must remove some edges. We remove this one, and we remove this one, and remove this one. For every removed edges, the number of colors will drop by 1. Because I will put here color 1, 1, 2, 2, 3, 3. We have k plus 1 vertices. So, the number of removed edges in order to obtain our graph G will be just 1. We have k plus 1 complete graph, we remove one edge, and then the colors drop from k plus 1 to k. So we have only these removed edges. Yeah. We remove just, why it always turns the eraser? I can apply once and then go back. Okay. So we obtain our graphs on k plus 1 by remove the, then we have actually like this. If we remove this, our graph looks pretty much like this. Our graph k minus 1 vertices, this is complete graph, complete. And 2 more vertices. And this is the unique removed edge. Let's say this was U and V, yes, we have U and V, yes. And this graph has really chromatic number equal to k. But there are 2 clicks of size k. The first click is this one, and the second click is this one. So if we remove one edge that is only in the first click, yes, if we remove this edge, chromatic number of this graph minus this edge, E, will be still K. So it will be not K critical, okay? This is the end of the proofs of the claim C, yes? And now we prove, now we go to claim D, yes? K critical graphs have no click cuts. Do we know what are click cuts? Click cut is like this. There are a set of vertices. So here's my graph G. This is a click. And when I remove this click from the graph, I will get 2 parts. This is my graph G1, and this is my graph G2, and this is the click C. So what I have, G1 intersection G2 is our click C, G1 union G2 is our graph G. I'll write it nicer. Okay. So, and because this is a cut click, we have at least one vertex here, at least one vertex. Okay. And we have also here at least one vertex, yeah. So when I remove the click C, I get two parts, maybe even three. And so everywhere I have at least one vertex. Now, if this is a if G is a K-critical graph, if G is a K-critical graph, if I remove these vertices here, if I remove these things, I will get smaller graph. And I will use K-1 colors here at most. Or if I remove the blue part, this part, I will remove at least one vertex, and what is left, it will be smaller graph. I can use K-1 colors or less. Now, in each of these two colorings, this is a click. What's meaning a coloring if we have click inside? We color all the vertices differently. So let's say this click is of size 3. Let's say we have the click is of size 3, and then we have some more and some here's some more, yes. So then I can, let's say, color here 1, 2, 3, and here maybe I use 4, 5, and so on up to K-1. I will not need K colors because this is a smaller graph. I can call it one color less. Also similarly here, I will start 1, 2, 3, 4, 5, and so on up to K-1. Okay. So I save some colors because here I use the same colors 1, 2, 3 here and here. I ask for these both parts. This implies that our chromatic number of our graph will be smaller or equal to K-1. Okay, and that's it. This is how we prove it. So in particular, when I apply this, I don't have critical graph who has hit a cut vertex. G is not critical. Okay, I don't have like this. I may have two cuts. This is one cut.
I got both the parts are K-1 correlated. But how can we conclude that the graph itself is at the most K-1 correlated?
So this needs K-1 colors. Let's say we have, I use here, let's say K is 10. K is 10. So I put 1, 2, 3 up to 9. Okay, this is a smaller graph, yes. And this part, the other part is also K-1. But I use the same colors here, 1, 2, 3 in the click. So I will go 1, 2, 3 up to 9. So I color this graph separately than these graphs, but here to be the colors the same. I do permutation of the colors. I use here 9 colors, I use here 9 colors. And there is no edge between that disturbs. I get I get coloring of the whole graph. Okay, this is it. We have two cuts, critical graphs with two cuts. But what we prove it now, if we have two cuts, here is no edge. Now let's no edge between U and V. Because if there is edge, it will be click cut of size 2. So we can have critical graphs which are with two cuts, but this could, in that case, U and V are not connected. Yes. There is also one theorem of Dirac, K critical graphs, are K minus 1 edge connected. But this is difficult. It will take like maybe at least 1 hour, maybe 2 hours to prove it. So we cannot afford to prove longer theorems because then we spend all the time just for one theorem. And it's not our purpose. Our purpose is to go through the theory and to prove easier task and harder one just to mention, to be aware that they exist, possibly apply for future work. Yes. Okay. Now I will mention several construction of critical graphs. But just for exercise, here my favorite critical graph. My favorite. Are we going to check it if it is really critical? Maybe I'm lying. You never know, so I'm from Europe. Okay, we have this graph. In order to be critical, what should we do? First thing, we should determine the chromatic number. Is it 3, 4, 5, 10? When we determine the chromatic number, let's say it's 10, then we should go through all subgraph and check it if every subgraph have chromatic number smaller or equal to 9. And if this holds, then our graph is staying critical. Okay, so what is the chromatic number of this graph? One, two, three, 4, or 5? 4, yes, exactly 4. So we can color it with 4 colors. 1, 2, 3. We can put 1, 2, 3. Just missing here only to put 1, yes, and that we color with 3 colors, but we are forced to put color 4. So okay, somehow we believe that chromatic number of this graph is 4. Now look this. This is very important. We have many subgraphs on one vertex, on 2 vertices, on 3 vertices, on 4. Should we check for all of them? We spend all day. For some of them are connected, some of them are not connected. Which one we should check? We should check for maximal subgraphs. In which are maximal subgraphs in this sense? Just remove only one edge. removing just one edge. You know, if I remove this edge and the chromatic number drop for 1, I don't need to proceed removing this one and this one and this one. They have smaller than 4. But for every edge, we restrict to subgraphs of type G minus some edge. And this graph is very symmetric. Do you agree? Because of symmetry, what do you how many things I have to check because of the symmetry? Because of the symmetry, if I check for this edge, I also have checked it for this. They are very symmetric, yes? So far 1. If I check for this, then I also check for this. If I check for this one, brown, then I don't need to check for this. This is because of the symmetry. And I have another, which color to use here? This is a single one, yes. So actually, we have the graph G. We can, for each of these 4 edges, we have to check if the graph means this edge, the color drops from 4 to 3, and then it's critical. So let's remove this. Can I set somehow when always to have? I have to go like this. I have to go like no. Let's say with the green one. If we remove this one, then I can put here color 1, 1, 2, 3, 3, 2, 1, and I color it. Okay. Let's say for this one. Now. Okay. Let's say for this blue one. This is a trick. Whenever I consider one edge, remove it, I will put on the end vertices the same color. 1, 1. Okay. Then I put here 2. Then I put 1 here. I can put here, I don't know, 1, 3. Okay. And then I can put 2, 3. Okay. Now, in similar way, I can deal with this one, and with this one is no big problem. So I see that this is really critical graphs. So you can try yourself for these two. For this one and for this one, you try yourself, remove each of these vertices, edges, and prove that we can color it with 3 colors. Okay. This is how we do, yes. Now we'll mention a few constructions, yes. First is Dirac construction. Do you know what's mean join operation? How many people here know what's mean join operation in graph? Okay, almost everybody. What's mean? So I have graph G1. This is like 2 graphs, G1 plus G2. This is join. So I take copy G1, copy G2, and then I copy this, connect every vertex of G1 with every vertex of G2. For example, if I have K3 here, and if I take K5 here, and I connect everything with everything here, so this is a join of C3 plus C5. Okay. And the reconstruction says if G1 is K1 critical and G2 is K2 critical, then what do you think? How much critical will be J1 plus G2? Yes. Do you believe me or should we prove it? What do you think? So White's K, first White's K plus 1, K, the chromatic number of this graph, some fast idea of the proof. White's K plus 1 plus K plus 1 plus 2. Look, we have here graph G1, graph G2, and all edges between. So for this part here, we have to use K plus K1 colors. And for this graph, we have to use K2 colors. Can we use color on the left side and on the right side in the same time? No, we cannot, because if I use this pinky color here and pinky color here, there is edge between them, then we're going to have monochromatic edges. So, chromatic number is K1 plus K2. What left to prove, if we remove here one edge, this is one option, or here one edge in between, or here inside, which is the same like the first case, our chromatic number always will drop by 1 in this. And this will be the case because when we remove here, these two I can color with the same color and save one color in G1. We can color this with K1 minus 1 colors because this is a critical graph because G1 is critical. And then I'll color rest normally. The same here. If I remove this edge, then I save here one color because I colored with K2 minus 1 color. Because I will color these two vertices with the same color. Again, I will color K1 plus K2 minus 1. And finally, if I remove one edge here, I can use normally color this graph, but put the same color here. And then I save again one color. And this is it. Okay. This is the reconstruction. Here is Hayosh construction. Oh, Hayosh. Maybe some strange thing construction. It says take G1 and G2 to be K critical, the same K. So before we had K1, K2, now we have of the same, okay? G1, they are vertex disjoint, yes? Take one edge here. So edge in G1 here. Then this graph, remove, then remove only edges, not end vertices. Identify x1 and x2 and third y1. And if I draw it nicely, it will look like so. This one, we put this new, and we remove this one. This edges are so we are running out of time, yes, but a new K critical graph, bigger one. So from we make new critical graph. So we discuss, and in this way we prove there are infinitely many graphs, bigger than equal to 4. Yeah? Now, do you see how to construct favorite critical graph? How I constructed my critical graph? Can somebody guess? K4, 2 copies of K4, yes? Yeah, okay, exactly. We take 2 copies of K4, blue, red. This is X1, 2, 1, Y2. We do, we, we this, move this, so that is kind of, we remove, uh, we remove this, maybe we take this one, we identify, and then we put the edge here. This is it, okay? Was this lecture too easy? I was supposed to mention more things, like to leave some of these arguments and to go faster, but I don't know the speed you are satisfied. So I can go faster next time, but we will be satisfied. Later will be some difficult theorems. We will only mention them. Sorry? Maybe we can cover a little bit more. This was chaos construction. How much time do you give me more? 1 hour. Maybe you can give 1 hour for lecture exercises, yes? And then we later do some more exercises. So this is one idea, because it's good to do more critical graphs, yes? Or maybe as a part of exercises, yes? No, but here comes now theorems. You cannot just like exercise them. They're difficult. We do the easy things now, yes? So there are some few more things I want to mention. So maybe I get 1 more hour. after the lunch. We will mention some more difficult things. We are not going to prove them because one proof it will be 2 hours, 3 hours. So we just mentioned them, which are very important to use them. Yes. Okay, that's it for now. Yes. So we make small break. Yes. And then I pick 1 more hour. Yes. Okay.